Okay, so hello everyone. I would like to introduce Deep Ray from USC, and he'll be telling us about deep learning based enhancements in computational physics. Over to you, Deep.
Thanks, Nishant. Thanks for the introduction. So what I'll be doing is I'll be presenting the work I've been doing over the last 4 to 4.5 years, where I've been trying to see how you can use deep learning-based tools in the context of computational physics. Okay, so here is an outline of my talk. So I hope you can all see the transition of the slides at your end. Okay, so here's an outline of my talk. So I will first begin by discussing or introducing 3 problems of interest, essentially to outline the kinds of problems I work with. And I will talk about certain computational challenges that exist with these 3 problems of interest. After that, I will briefly introduce neural networks for those who haven't seen neural networks before explicitly. And then I will show you how you can use deep learning to overcome the challenges in the problems of interest. And I'll end with some concluding remarks. Okay, so the first problem of interest is handling discontinuities. And this is going to be in the context of conservation laws. So conservation laws are modeled using hyperbolic PDEs. And typical examples are the shallow water equations in atmospheric and oceanic modeling. You have the compressible Euler equations for aerospace problems, and the magnetic hydrodynamic equations in astrophysics, say if you want to simulate the collapse of a neutron star. Now, what's well known about solutions to conservation laws is that you have discontinuities in finite time, even if you start off with a nice smooth initial condition. So here I demonstrate this for the simple scalar-Burgers equation, where you start with a sine wave, but you end up with discontinuities in finite time. And this becomes important when you're designing higher order methods to approximate solutions to conservation laws. And the reason why this becomes important is the following. So say you want to approximate some function using a smooth basis. Now you could either have a function which is nice and smooth, like the one on the left, which is a sum of sine functions, or you could have a function with a jump. And for the smooth basis, you could take any smooth basis that you like. You could take the Fourier basis, you could take Legendre polynomials, Lagrange polynomials, whatever you like. Now, as you keep adding more and more basis elements, you would expect that you would end up getting a better approximation, the target function. And this, in fact, is true for something smooth, where you eventually do converge to your target function. However, if you have some kind of a jump discontinuity, although you do reach close to the target function, you introduce these spurious oscillations, which are known as Gibbs oscillations, which can pollute your entire solution. And this can very quickly destabilize your numerical solver. For instance, if you're solving for compressible Euler equations, where you have positive density and pressure, these kind of oscillations can lead to negative density and pressure, and your code just blows up. So there are several methods that have been developed over the last few decades in the context of higher order schemes for conservation laws to detect and control such spurious oscillations. The challenge is that most detection and control methods that exist have problem-dependent parameters that you need to prescribe. And there's no way of a priori knowing what these problem-dependent parameters should be, and they must be empirically determined. So this is the challenge in solving using higher order methods for solving conservation laws. Now, the next problem of interest is what I call many query problems. For instance, say we are trying to solve some parameterized model, which is coming from an ODE or a PDE, or maybe even an integral equation, and let's denote this by this curvy M. And the parameters are denoted by a vector Z, which could be parameterizing your initial condition, your boundary condition, maybe some design parameters, or whatever you like. And from this model, you end up getting some solution U, which is of course also parameterized by Z. And say you are interested in not just the solution, but some observable or some functional of the solution. Let's denote that by L. And this could be, for instance, if you're solving the compressible flow equations, this could be the lift and the drag experienced by an airfoil if you're doing a flow past an airfoil. Or if you're doing tsunami simulations, this could be the wave height of the wave that you're simulating. Now, what's true in most realistic problems is there is always uncertainty. So there could be uncertainty in measuring this parameter vector Z, and this will induce some uncertainty in the observable L. So we want to be able to estimate the uncertainty in L. And one nice way of doing this in a non-intrusive manner is by using Monte Carlo simulations, where you assume some prior distribution on this parameter Z, and then you can approximate all sorts of statistics of the observable using Monte Carlo averaging. Now, the challenge here is the following, that for typical Monte Carlo, the error in approximating statistics goes as order 1 over square root of m, where m is the number of samples you're using. And that means if you want really good approximation of the statistics, you need many, many samples. Now, for most realistic problems, even a single solve of this model can be very expensive. So to ask for many samples can be prohibitively expensive. So this is a challenge that exists with uncertainty quantification for such a setup. Finally, the third problem of interest is going to be inverse problems. So say we are considering some forward direct map F that goes from a domain omega x to an omega y. So this could be, say, the solution map for a PDE solver. Now the task is, given some noisy measurement or output of this map F, which I denote as y, which is fx plus some eta, where eta is some noise, which is maybe modeled using Gaussian noise or some other random distribution, that given this noisy measurement, we want to be able to infer x that generated this measurement. Now, there are various ways of doing this. One way of doing this in a principal manner is using the Bayesian approach, where you assume that x and y are modeled using random variables, and then you can pose using Bayes' theorem that the posterior distribution of x given the measurement y is the likelihood of the measurement given some x times the prior distribution of x divided by the marginal of y. And this marginal of y is known as the evidence term. And for most high dimensional problems, it's very difficult to compute. So you typically work with a proportionality relation where the posterior is proportional to the likelihood times the prior. And the specific case where you're working with additive noise, this likelihood term you can write in terms of the noise distribution as p eta y minus fx. Now, if you have this this expression for the posterior, you can solve this using Bayes' approach, where you would first have to construct in some suitable way the prior distribution of x. And this you have to construct based on some prior data or snapshots that you have about x, or maybe some constraints that you know about x. Next, once you have this expression on the right-hand side, you could use Markov chain Monte Carlo to construct a suitable Markov chain whose stationary distribution will converge to the target posterior distribution. And you would typically simulate this chain for a finite length. So let x1 to xn be the elements of this chain. Then you can use these elements of the chain to evaluate all sorts of empirical statistics of the quantity that you're after using Monte Carlo. So this is how you would solve an inverse problem using a Bayes' theorem or the Bayesian approach. But the challenge is the following. A Markov chain Monte Carlo can be very expensive to use if the dimension of the x that you're trying to infer is very large. And I denote the dimension of x as nx. So if nx is very large, a Markov chain Monte Carlo can be prohibitively expensive. And the second challenge is, if you're given data which is very complicated, it can be very hard to characterize it. So typically you could use something like a Gaussian prior in your Bayes approximation, and that would be very convenient. However, what if your data looks like this? It could be this microstructure like examples, or it could be these handwritten digits, which is known as MNIST digits in data learning and data sciences, or it could be these images, which is known as Shepp-Logan phantoms, which are modeling the human head. So if you're given data which looks like this, it's going to be very hard to represent this data using something as simple as a Gaussian prior. So in Bayesian inference, the two challenges are, first of all, MCMC is very expensive and the dimension is large, and you need to sometimes characterize really complicated data. Now, in each of these three problems of interest that I introduced, they have a common theme. There is some underlying algorithm that generally works well, but there is some kind of a computational bottleneck. And the way I'll be using deep learning is I'll be surgically removing the computational bottleneck and introducing a deep learning toolbox to overcome these challenges. And this will be the main theme of how I'll be resolving these challenges for the problems of interest. Now, before I show you how you can do this, as promised, let me give you a quick primer of neural networks. So in neural networks, it's important to understand what is it that you're actually trying to do. You have some underlying unknown function f, which takes an input x and gives you an output y. And all you know about this f is perhaps this data set s, which is the pairwise data of x and the corresponding value of the function at that particular x, which is y. And just from this data set, you want to be able to get a good approximation of this target function f. And one way to do this is using neural networks. And in particular, I'll be talking about one specific kind of neural network architecture known as multi-layer perceptrons. So in a multi-layer perceptron, you have a number of these computing units, which are denoted by these square terms over here, which are called the artificial neurons. And these neurons are stacked in consecutive layers from left to right. And the way it works is you will feed it some input in the left, and it passes through all the layers. And finally, it'll give you a corresponding prediction y hat. Now, within each layer, the following happens. You have to define some weight matrix W and a bias vector B. And using this W and B, an incoming vector from the previous layer undergoes an affine transformation, following which we apply a component-wise nonlinear activation to this vector, and then we pass this vector on to the next layer. So this affine transformation followed by a component-wise linear activation happens in each of these layers. So mathematically, you can write the entire neural network as as alternate compositions of affine transformations followed by component-wise activations. And this is what the whole multi-layer perceptron will look like. And this is parametrized by this theta, which are the trainable parameters, which is nothing but all these W's and B's, which are the weights and the biases of your network. So then the task becomes somehow trying to figure out what these weights and biases should be so that the neural network approximates your underlying target function f in a suitable manner. Now, in terms of the activation function, there are many options out there. I only list 6 of these. Some of the more popular ones is this rectified linear unit, which is simply piecewise linear, or a leaky version of that, which has a small slope even when you have negative values. And something that's become even more popular in the last 1.5 years is a sine activation function. But you can in principle use any of these. Typically, you would avoid using the linear activation function. Otherwise, your entire network reduces to a simple affine transformation. But you could use some kind of nonlinear activation function. So we have a neural network. We have this data set. And now we want to be able to train the network to approximate the function f. And for that, you have to define some suitable loss function to measure the discrepancy between the prediction and the true output. So you could, for instance, take the mean square error loss to evaluate this discrepancy. And this is a function of these parameters theta. And then you have to suitably optimize to minimize this loss function. You could use something like stochastic gradient descent, or a more commonly used method is Adam optimization to find theta star that minimizes this loss function. And then you plug in this theta star in your neural network, and that will be a good approximation of your target function f. Now, this is not the end of the story because you've just trained the parameters theta, but the network also has a lot of hyperparameters. So this could be, for instance, the width, which is the number of neurons in each layer, the depth, which would be how many layers are actually sitting in your neural network, what kind of activation function do you want to use, what is the best optimizer to use for your problem, how do you stop the optimization training process, what kind of loss function do you want to choose? So mean square error might be good for regression type problems. Let's say you're trying to do something like classification, then mean square error is not a good function. So you have to choose your loss function accordingly. Then you have to make sure that while training, you've regularized your training process in a suitable manner so that your network does not overfit the training set. Because if it overfits the training set, it will not perform well outside it, and it will not be able to generalize well. That's the term that is used for neural networks. And of course, you also need to figure out how to construct a suitable data set. And finally, something which I think is very important is understanding, having reasonable expectations from your network. While these deep learning algorithms work well in practice and can solve all sorts of problems, it doesn't solve every single problem. So you need to tune the expectations you have from the network you're training. Now, the good thing about multi-layer perceptrons is there are a lot of universal approximation theorems that exist about them. And they start from all the way in 1989. And in fact, even till recently this year, there's been some theorems that have been developed, which tell you that given some target function f, which falls in some function class, you can find a neural network that approximates that function in a suitable norm up to an epsilon approximation. In fact, some of the later theorems also tell you how large this network must be to get this epsilon order approximation. Now, multi-layer perceptrons is the simplest form of architecture that you can use for deep learning. There are more sophisticated network architectures that exist. For instance, you can use something like convolution neural networks, which is very good when you're handling data which are images. You could use residual neural networks. You could use U-nets, which are useful when both your input and output are images. For instance, if you're solving a PDE on a 2D grid, and then your input and output could be 2 fields on this grid. So this could be approximated using a U-net. You could use autoencoders, which are useful for reducing the dimension of some field. And you also have something called generative adversarial neural networks, which are called Gans. And these are useful in learning the distribution of the underlying data set. And I will come back to GANs later in my talk. So this is all about neural networks. Now let's move to actually seeing how you can use deep learning to overcome the challenges I discussed in the first part of my talk. So let's go to handling discontinuities and conservation laws. Just to recall what we're trying to do here, we have some conservation law. Say it's a scalar conservation law in 1D for simplicity, and we want to develop a high order method to approximate the solution. You could do something like a finite element type method, where you would first discretize your spatial domain into a number of cells, and then on each cell, you will use some polynomial basis to locally approximate the solution. Say this is what the solution looks like at some time instant. Now, in some of these cells, you see these wiggles that exist. These wiggles could denote these spurious oscillations because of the presence of a discontinuity. So one way to overcome these, to suppress these oscillations is in the context of at least discontinuous Galerkian schemes, is by limiting the solution in these bad cells. So the first step would be actually finding out what these bad cells are. And these are known as troubled cells, cells which contain discontinuities and could possibly have these spurious oscillations. That's step one. Now, say you have some mechanism to detect these troubled cells. The next step would be to replace the high order representation of the solution in these particular cells with a low order representation, maybe a limited linear representation, and that is able to take care of these spurious oscillations. So you have to first detect the cells, and then you have to limit the solution. Now, of course, there are lots of detectors that have been designed in practice, but the challenge is that they actually require the prescription of problem-dependent parameters. Now, if you pick this parameter incorrectly, two things could happen. Either you flag insufficient number of cells, so you miss some of the troubled cells, so your oscillation will reappear and your scheme might become unstable. On the other hand, you might end up flagging excessive number of cells. So you don't not only flag the true troubled cells, but also cells where the solution is smooth. So now you'll be actually limiting the solution in those cells. So you're increasing your computational cost. And limiting can actually be very expensive for high order methods. And furthermore, limiting can also reduce the local accuracy. So you'll also lose accuracy in smooth regions. So these methods work well as long as you can correctly flag these troubled cells. And this is what we can do actually without having to tune problem-dependent parameters using a neural network. So what we did is we trained a multi-layer perceptron to classify cells in a mesh as good cells or troubled cells. The input to this network would be the solution in a given cell, or maybe on a local stencil. It was a network with 5 hidden layers, and we used leaky Rayleigh activation, and the output of this network would be a number between 0 and 1. So you can see this output as the probability of that particular cell being a troubled cell. So if this value was greater than 0.5, we would flag it as a troubled cell. And for the training set, we never actually used solutions to conservation laws. We made use of our domain knowledge to understand what solutions to conservation look like at a local scale. So we looked at functions like this, which is a sine function, which is nice and smooth. We use functions with a corner, where the corner is a problematic area. And we use functions which have a jump discontinuity. And we generated a lot of these functions, which are canonical representation of solutions to conservation laws locally. And we sampled from them. And whenever you would sample from a smooth region, you would label that particular sample with a 0, denoting a good cell. But whenever you would sample from a bad region, you would label that sample as 1, which is a troubled cell. So you have this labeled data set that you create from canonical functions, and that's what you train your neural network on. Now, this training is agnostic of any specific conservation law, because we never actually use solutions to conservation laws. And this network is trained offline, and then the same network is used for all conservation laws. And I'll demonstrate how this works with 2 examples. So we trained a multi-layer perceptron detector for 1D problems in the context of discontinuous Galerkian schemes. And this we're trying to solve here the Burger's equation using a DG scheme. So this is what the initial condition of the Burger's equation looks like. So it has some smooth regions, and it also has some jumps. In the bottom plot over here, what I will show you are the various cells that are flagged as troubled cells by the network. And this is X on the X-axis and time in the Y-axis. You'll see how these cells are flagged as a function of time. And ideally, the network should be able to track the discontinuities as they move in the mesh. So let me see if I can create this video. So you see, as the discontinuities are moving, the network is tracking the discontinuities. And whenever new discontinuities start to form, the network detects it and starts tracking that. but it's not flagging any solutions anywhere else where things are nice and smooth. Now, like, compare this method with one of the traditional detectors. For instance, you can use something called the Tvb detector, which has a tunable parameter m. This is proposed by Cogburn and Shu, but of course, you don't know what m to pick a priori. So we took 3 different values of m. M is 10, 100, and 1000, and we tried to solve the same problem with these 3 parameter values of m. If you take m is equal to 1000, you had spurious oscillation. So this m was too large and not good enough. However, if you took m100 or 10, you get oscillation-free solutions. But the good thing is that with the neural network, you didn't have to tune any such parameter, and you still had oscillation-free solutions. So this is in 1D. We've also tested it out on various other conservation laws, and it's quite robust. Now, we also managed to do this for 2D problems, where we trained a network to detect travel cells on unstructured triangular grids. And to demonstrate how that works, we can look at the 2D Euler equations that we are trying to solve for the density to 2 momentum components in the total energy, and show you the example of a shock vortex problem. But what you have is you have a smooth vortex sitting on the left, which moves slowly to the right, and you have a shock discontinuity sitting at x equals 0.5 that moves slowly to the left. And at some point, the smooth vortex has to pass through the shock and reappear on the other side. So you have to deal with shocks and smooth structures at the same time. Now on the top, I'm showing the contour plots at time t is equal to 0 currently. And you see that these are the contour lines of the shock, and that's the contour lines of the vortex. And on the bottom plots, I'm showing you the cells in 2D space that are flagged as trouble cell by the detector. So the first 3 are for the Tvb detector with different values of m, and the last one is the multi-layer perceptron. Now you can already see that all the Tvb detectors are flagging the discontinuous cells in the discontinuity, but are also flagging cells in the smooth vortex. So this shouldn't be doing, but the detector at time t is equal to 0 is not flagging cells in the vortex. Now I want you to pay attention to this plot and see how cells are flagged by the multi-layer perceptron as the solution evolves. So you see that as the vortex passed through the shock, it continued to essentially flag cells in the shock, which led to a very nice recovery of the vortex on the other side. However, with the other Tvb detectors, you ended up flagging too many cells in the vortex, and that led to a very smeared out vortex on the other side of the shock. So you can use trouble cell detectors. You can use multi-layer perceptrons as trouble cell detectors and do this in a parameter-free, problem-dependent parameter-free way. Now, this was trouble cell detectors. We also did similar work to control spurious oscillations, but you can also do this by adding an artificial viscosity term to the right-hand side of your conservation law. But then the challenge becomes to tune this viscosity coefficient mu AV based on the local solution regularity. So if it's nice and smooth, this mu AV should be small, but if you have discontinuities, they should take a large value. And there are methods in which you can pick this mu AV, but they're problem dependent. They depend on problem dependent parameters. So we trained neural networks to give you this mu AV directly by looking at the local solution. So we trained a multi-layer perceptron to estimate the artificial viscosity in discontinuous Galerkian schemes. And we also were able to train multi-layer perceptrons to predict the artificial viscosity in global spectral schemes, where your basis is defined on the entire domain and not on each single cell. And we were also able to use multi-layer perceptrons to do P adaptation in the context of DG schemes. Of course, I'll not have time to talk about these in detail. I'll be happy to talk about them more after my talk. So this was the first application where you're controlling, you're handling these discontinuous solutions using neural networks for higher order methods for conservation laws. Now let's come to the next application. The next application were these many query problems. So to remind you what we're looking at here, we have some model M that is parameterized by some Z, and that gives you a solution. And the Z could have some uncertainty in it. So we model it using some prior distribution view. And now we want to be able to measure uncertainty in some observable, which is a function of U. And we could, for instance, look at this example where we're trying to do a 2D Euler simulation past an RAE airfoil, where we solve this using a finite volume solver, where this is, say, the grid around my airfoil. And that's, for instance, one of the solutions for some realization of Z. Now, a single simulation of this for some single realization of Z can take up to 7 hours on a cluster. And this cost becomes even higher if you're solving 3D problems. So it becomes almost impossible to get a lot of samples to do Monte Carlo simulations with this. So the task is the following. We want to be able to measure the push forward measure mu hat, which is the measure pushed forward by this this observable map L. And then we want to be able to evaluate statistics with respect to it. And now we will do this in 2 steps. First, we will replace the map that's taking parameters to the output of the observable by a network surrogate L star that can directly take Z to the corresponding value of the observable. And then we will use a network surrogate L star to approximate this push forward measure mu hat using Monte Carlo. But it's important to remember that you might be working in a low regularity setup, because if U is a solution of a conservation law, then U could be, because of shocks, could be maybe BV regular only. And if L is an integral of this solution, then you can maybe expect L to be at most Lipschitz continuous. So you have to work with functions of low regularity, which you need to approximate using neural networks. And secondly, you have to work in a data poor regime where you don't have many samples to train your network on. Now, before I show you how you can do this, let's set a baseline model to compare with. So the baseline model I'll be using is Quasi Monte Carlo, where you begin by first selecting JQMC low discrepancy sample points. Say these could be Sobol points or Hartle points. This is different from choosing IID samples in omega z. These low discrepancy points actually help spread and cover this domain omega z in a better manner. Now, for each of these zi's, you would compute numerically the solution uzi and then evaluate the corresponding observable value at that zi. And then to approximate the statistics of L, you first approximate the push forward measure as an average of Dirac measures centered at LZI, and then you can plug this in to the formulation of any statistic, and you'll end up with the usual Monte Carlo average. Now, this is our baseline Quasi Monte Carlo method. Now, in the next slide, I'll show you how you can use deep learning, and you'll see in the colored lines what is the difference between the baseline method and what I call the deep learning QMC algorithm. So once again, you'll start off by picking JDL low discrepancy sample points. And now you will only pick the first n of these points, where n will be much, much smaller than JDL, and you'll use that to form your training set. Now, for every single ZI in this training set, you will compute your numerical solution and evaluate the value of the observable. And this will give you this pairwise data set of ZI and LZI. So you'll train your neural network L star on this training set. And then you will approximate the statistics using L star, where you approximate the push forward measure, again, as an average of Dirac masses sitting centered at L star ZI. But what's important to understand here is this L star, you're now simply querying the network once it's trained. You no longer have to solve a PD solver and get the value of L star. You can simply query the network and you get this approximation. Now, to see whether this is actually helpful, we can analyze the DLQMC algorithm. And to do that, we have to define some suitable metrics. First, we define the generalization error of the network, which essentially measures how well the network approximates the target observable map. Next, we define a metric to measure the discrepancy between the true push forward measure and the approximation of the push forward measure. And we use the Wallerstein-1 metric to do that. And then we define a speed up over the baseline QMC algorithm in the following manner. So for any epsilon positive, say you have a QMC algorithm and a deep learning algorithm, both of which give you an order epsilon approximation in approximating the push forward map, then the speed up is the cost of the baseline QMC algorithm over the cost of DLQMC. And what you can prove is, firstly, if the generalization error of the network is of order epsilon, then the approximation error in measuring the push forward measure in the Wallerstein-1 distance will also be of order epsilon. Furthermore, if say you need JQMC samples to get the same order of approximation using the QMC algorithm for the push forward measure, then you have this relation for the speed up, where n is the number of training samples, JQMC were the number of samples you need for the QMC algorithm, C is the cost of generating a single sample, while C star is the cost of evaluating a trained network. So you'll have a speed up if, first of all, you have low generalization error. That means you have a well-trained network. And here, using these low discrepancy sequences plays a big role, because there is follow-up work that shows that that actually helps reduce generalization error significantly. Next, you must ensure that the number of training samples is much smaller than JQMC. If that's not the case, then you might as well just use the baseline QMC algorithm to compute the statistics. Why do you want to train a network and increase the cost? And finally, you need to ensure that the cost of evaluating a trained network is much smaller than actually computing a single sample. And I'll demonstrate this with a numerical example. So let's look at this flow past an RAE airfoil, where we're solving it using a finite volume solver, and our observables are going to be the lift and the drag experienced by this airfoil. My Z is going to be 6-dimensional, which will consist of 2 shape variables and 4 operational parameters. And to train the network, I will take the first 128 Sobel points and solve the finite volume solver and get the value of the observable, and that will be my training set. And for testing, I'll choose 1001 Sobel points. And the way we train our network is, instead of training a single network, we train an ensemble of networks where we kind of look at all sorts of hyperparameters to figure out what hyperparameters gives you the best network for lift and drag. And for the best performing networks, for lift, you end up with an error of less than 1%. And for drag, you end up with an error which is less than 2%. And these are very encouraging errors, given that you've only trained on 128 samples to begin with. Now, what you could do is you could take these best performing networks and evaluate it for all the Sobel points and see how good the predictions are. So you can make this plot of the actual value versus the predicted value for lift and drag. And this cluster plot, the closer it is clustered near the diagonal, the better the prediction. So we have good predictions both for lift and drag. And what you can also do is you can take all these predictions and make a histogram out of that. And you can compare it with the histogram of the true values. And this is giving you an approximation of the underlying distribution for lift and drag. And you see that the predicted histogram and the true histogram seem to match up very well, both for lift and drag. And finally, in terms of the cost, the time required to generate a single sample is around 7 hours, which is approximately 24,000 seconds. The time taken to train a single network is 700 seconds, but the time needed to evaluate a trained network is in the order of microseconds. And because of this, we can numerically show that we have a speed up of almost 6 for the lift and a speed of almost 8.5 for the drag compared to the baseline QMC algorithm. We also tried this out for the usual Monte Carlo algorithm, where you choose IID points. In that case, you actually get 2 orders of magnitude speed up over the baseline Monte Carlo algorithm. But here you won't expect much more than this, because QMC is already a pretty good algorithm, but you still get a reasonable speed up. Now, since you're able to approximate these parameters to observable map very well using these deep learning surrogates, we were also able to extend this and you do some PD constraint optimization, where we devised an active learning ISMO algorithm that can actively learn and optimize, say, the shape of an airfoil starting to some base shape, with the task of minimizing the drag while keeping the lift as constant. And you could parameterize the shape using some Higgs-NA functions. This lead to a parameterize of dimension 20. And then we actually ended up showing that you could reduce the drag by more than 50% while keeping the lift nearly constant. And we also have some theoretical estimates to show the convergence of this ISMO algorithm. Again, I'll not be able to talk about this in detail, so I'll be happy to talk about this offline. Now, with that, I come to the third part of the talk, which is solving inverse problems. Could I get a check on the time, Nishant?
Yeah, so you have about 14 minutes left. You have plenty of time.
Okay, fine. All right. So let's go to inverse problems. All right. So to remind you, the challenges that exist with inverse problems in doing Bayesian inference is we have this relation for the posterior in terms of the likelihood and prior. And if you want to kind of sample from the posterior using MCMC, this is prohibitively expensive when X is high dimensional. And it's problematic to represent priors when the prior is given in terms of complicated data like this. And I will show you that you can overcome both these challenges using a specific type of deep learning algorithm known as generative adversarial networks. So what are generative adversarial networks, or GANs? These were designed by Goodfellow et al. In 2014 and were designed to learn and sample from some target distribution Px. And this actually consists of 2 networks, not just one network. The first network is known as a generator, while the second network is known as a critic. The job of the generator is to create fake samples of X. So it takes as input a latent variable Z, whose dimension is much, much smaller than the dimension of X. And Z is typically sampled for some simple distribution like a multivariate Gaussian. So it takes in a Z and gives you a fake X tilde. And now the critic its job is to distinguish between fake samples and real samples. So whenever it encounters a real sample, it assumes a large value, but whenever it sees a fake sample, it takes a small value. So the critic's job is to catch the generator, while the generator's job is to fool the critic. So the way these networks are trained, they're trained in an adversarial way. So they're battling each other, and that's why they're called generative adversarial networks. And I'll look at a specific instance of GANs, known as Wasserstein GANs, which is introduced by Arjovsky et al. In 2017, where the objective function, which is the function of the generator and the critic, is given by the expectation of the critic evaluated at x, where x is sampled from the true distribution, minus the expectation of d or g of z, where z is sampled from the latent distribution. So the first term here is basically for the true samples, and the second term here is for the fake samples. So the critic will try to maximize this objective function, while the generator will try to minimize this loss function. So you have to solve a min-max problem, and under the constraint that D is 1 Lipschitz, you can obtain G star and D star that solve this min-max problem. So assume you're able to get this G star and D star, then what you can show is that the optimal generator is actually minimizing the Wasserstein 1 distance between the true distribution and the push forward of Pz by the generator. And if you're able to converge in the Wasserstein 1 metric, you have weak convergence, which means that your statistics of the true and fake samples will match up. So this is the sense in which things converge for a Wasserstein GAN when you're able to train it appropriately. Now, how do you want to use GANs for Bayesian inference? We would like to use GANs to actually use it as the prior for a Bayesian inference problem. So assume what we are given is just a set S of X's, which are taken from the prior distribution. So that's all we know about the prior distribution. And we have access to the direct map F. So if you're solving a PD, this could be the forward map, which is known either exactly or approximately. We know what the noise distribution P eta is, and we are given some noisy measurement Y. Then given this, we want to determine the posterior distribution of X given this measurement Y and evaluate statistics with respect to it. And we can do this in 3 steps. Step 1 is you take this data set S and you train a Wasserstein GAN to generate more samples of the same type. And let's say the generator we get out of that is called G star. And assume that we have a well-trained GAN so that the optimal generator satisfies this weak relation, which relates the statistics of the X when it's sampled from the prior and when Z is sampled from PZ. And we also assume that the forward map F and P eta are continuous. Now that these assumptions, you can transform this weak relation on the prior to a weak relation on the posterior, where the expectation of phi of X, where X is sampled from the posterior of X, is equal to the expectation of phi of G star of Z, where Z is sampled from the posterior of Z, where the posterior of Z has a very similar expression to that of the posterior of X, which has the likelihood term here, and you have this prior, which is essentially going to be like a multivariate Gaussian. So this you know exactly how to represent. And what this is showing you is to sample an X from the posterior of X, it's enough to sample Z from the posterior of Z and push it through the generator G star. So once you have this set up, now you can do MC for the Z variable, which is a much lower dimensional object. And you can generate a chain in Z using MC, so Z1 to Zn. And then you can evaluate statistics using Monte Carlo, where you simply push the Z through the generator and then use Monte Carlo averaging. So what do we gain by this method? First of all, now you're able to represent complex priors, assuming you have this data set S. And secondly, since you've reduced the problem to the low dimensional space of the latent variable, MC becomes computationally tractable. Now I'll demonstrate how this works through an example. So let's look at this PDE, which is an elliptic PDE, where we're trying to solve for U, which is a temperature field, given some conductivity coefficient kappa, some source term, and assuming a Dirichlet boundary condition. And the inverse problem is, given a noisy management Y, which is the noisy temperature field U on some 2D grid, we want to be able to infer X, which is the nodal values of kappa on the same grid. The forward map will be this nonlinear PD solver, which is implemented in Python using Phoenix, and we assume the noise to be Gaussian IID. So first, you have to assume a prior on kappa, and let's assume the prior on kappa is given like this. So it's actually given by this microstructure form. This is what the data for kappa looks like. This is on a 64x64 grid. So the dimension of X is 4096, and we train a GAN to generate samples like this, and using a latent variable of size 100 only. And these are what the generated samples look like. These are the training samples, those are the generated samples, and in the eyeball norm, they look very similar. Now with this trained GAN, we plug it into our Bayesian formulation, and we start with a new kappa, which was not trained on. We use the PD solver to find the temperature field, add some Gaussian noise to it, and then this becomes our measurement. And with this and the GAN as prior, we evaluate the map, the mean, and the standard deviation. So you see the map is very close to the target kappa. The mean is a smeared out version of the map, and the standard deviation takes this peak value along the edges of these structures over here. Now, what I want you to focus on are these red rectangles over here, and you notice the map is actually off in these rectangles near the boundary. And this is not perhaps strange, because the temperature field near the boundary is primarily determined by the Dirichlet boundary condition and not so much by the conductivity. So the signal over here is low, so the recovery of kappa might be poor. But however, the good news is if you look at the standard deviation in these regions, that is also high. So this is telling you that I have a reconstruction, but it's also telling you which parts of this reconstruction to trust and how much to trust it. This is kind of one of the advantages of using Bayesian inference, because it gives you a map, but it also tells you how much to rely on the reconstruction. You can also compare this reconstruction to a more standard Tvb regularization-based method, where you can directly estimate the map. And with that, you do not get a very sharp reconstruction. In fact, you don't even get the right intensity of the kappa that you're after. So here we do this for one single kappa. Here's another kappa we do it for, and again, it works just as well. And the standard deviation gives you an idea of where the error could be the highest in the reconstruction. So with that, I come to the conclusion of my talk. So what I've shown you is that you have traditional algorithms, and these can have computational bottlenecks. This could be perhaps having to determine the problem-dependent parameters, which you cannot assess a priori, or maybe there is some component of your method which is very expensive to compute. Now, you can judiciously integrate deep learning algorithms into this so that you can overcome some of these computational challenges. Deep learning can be used for classification, like for a trouble cell detector. You can use it for regression problems, for instance, to approximate the map going from parameters to an observable, or also to approximate the underlying distribution of some data set. And the advantage of using deep learning in this way is that once you've trained a network for a particular application, you do not have to tune any parameters after that. You can use it as is out of the box for that particular application. And for some of these cases, you can theoretically show why the network actually works the way it does. So you have some theoretical estimates and some theory to back up the performance. So now, before I end, I will also like to mention a few other things that I do, which of course I didn't have time to talk about. First of all, I also work on traditional higher order solvers for flow problems. For instance, I developed these entropy stable schemes for conservation laws and kinetic energy preserving schemes for Euler equations. This was primarily the work I did as a PhD student at TIFR CAM. But more recently, I've also been designing higher order discontinuous Galerkin methods to solve two-phase flow problems through realistic rock structures in the presence of a surfactant. And these kind of models are very useful for the oil industry. In fact, one of the projects I did was funded by Shell, and they wanted to have a high fidelity solver that can quickly do simulations of this form through rocks. I also do other applications in machine learning and deep learning. For instance, I've trained neural networks to approximate Riemann solvers for conservation laws. We've also been able to show that neural networks can be used to represent these ENO reconstructions, which routinely appear in high order finite volume methods for conservation laws. I've also done some reduced order modeling using deep learning. Now, I showed you in this talk how you can use a GAN as a prior in the Bayesian update step, but there is another way in which you can use a conditional GAN to directly approximate the posterior distribution and sample from it. And the advantage of that is, if you do this, you completely get rid of MCMCs. You can directly sample from the posterior and evaluate statistics. We've also used these kind of techniques to do image imputation for medical imaging problems. And I've also used more traditional machine learning techniques like decision trees and random forests to do data-driven predictions for COVID-19 severity, which has been even more important in the last 2 years, and also to look at bladder cancer recurrence amongst patients. And these were some undergraduate projects that I supervised at USC. Now, moving forward, there are many things that I would like to do. I mentioned a few of the things I would like to do soon. One of these is, for instance, the neural networks are trained to detect trouble cells. These have been trained on 1D grids, on 2D grids. But I would like to extend this to full 3D hybrid grids, where you're not just working with tetrahedrals, you can have all sorts of elements in it. And this becomes challenging because for 3D simulations, it's very hard to, the flow patterns are very complicated. So it's not going to be easy to generate a suitable training set for this. And secondly, if you use a hybrid grid, what you're also allowing for is an input which has a variable input dimension. And neural networks as it stands cannot handle variable input dimensions. So that will be a challenge to look into. And apart from deep learning algorithms, I also want to use more traditional machine learning techniques to do these trouble cell detectors, because the things like decision trees and random forests can also give you automatically some feature importance about the input that's going into these algorithms, and can perhaps tell you, maybe you don't look at all the solution in the cell, you look at particular elements of the solution of this input, and that's good enough to create a robust trouble cell detector. Now, I also want to do some applications in deep learning which are driven by physics. One of this, of course, includes this GAN-based strategy, but we'll kind of extend this to other problems like data assimilation or radar sensing. And what has been recently shown is if you're able to embed the underlying physics of the model into your network architecture in some suitable way, either in training or in the architecture itself, for instance, something that's done in physics-informed neural networks or deep operator networks, you can get a network that's more robust, gives you better results, and you can also reduce the dependence on a large data set. So you can get away by training on a much smaller data set. And this is essentially what you have to do in most realistic problems, because you can't work with a large data set. And finally, I would also like to work towards bridging the theoretical gap between the deep learning algorithms used in practice and to explain why they work the way they do, and build reliability in the community about using such techniques for computational problems. And finally, there were a lot of problems I investigated during my doctoral dissertation regarding higher order mimetic schemes, for instance, entropy stable schemes. There are various extensions possible for the work I've done, and I would also like to investigate that moving forward. So with that, I end my talk, and I'll be happy to take any questions.
Thank you very much, Deep, for this wonderful talk. Are there any questions from the audience?
Can I ask a few?
Please go ahead.
All right. So let's begin with the first part,
Okay.
in which you were talking about the tagging of the cells.
Yeah.
So in the tagging of the cells, you are basically preparing, or you're training your network, machine learning algorithm or deep learning algorithm to identify two types of non-smooth things. So one was jump, the other was a cone.
Corner,
So,
exactly. Yeah.
Right. So you said towards the end of your talk that you want to also try this cell detection in higher dimensions.
Yeah.
You said 3 dimensions, but I suspect even in 2 dimensions is going to be a problem, right? Because in 2 dimensions, I mean, when the domain is 2-dimensional, you'll run into trouble because there are several types of non-smooth things that you'll have to identify. So then, I mean, I suspect like one has to do quite a bit of work to just
absolutely. So when we trained the network for 2D, we actually looked at more types of discontinuities. If we looked at, in fact, instead of a simple corner, you would look at a corner which is along a line or a curve.
Right.
You would look at discontinuities, which could be 4 types of discontinuities which have discontinuities along 2 intersecting lines. So we looked at a richer data set. So the point is that, of course, going from 1D to 2D, you have to take a much richer data set. Now going from 2D to 3D, it's going to be even richer, and it's already hard to visualize things in 3D.
Right. So my question basically is that if you really want to just continue along the same thought process, then how good is it, numerically speaking, in terms of the dimension? Because if the dimension is growing, because the things that you have to train your data set on, that is increasing and very rapidly. So
that's why you have to kind of figure out what kind of canonical discontinuities or local features you could expect to see in your solution. So you would not look at the entire solution, but look at it locally. And locally, you could reduce the structure to something simpler. Instead of, if you look at a line locally, it's maybe just a straight line, right? Instead of a curve. So
I
you
see.
could locally
So
look at things and kind of determine what these canonical
I
functions
understand.
should
So
be.
you basically want to continue with the same thought process, right?
One or the other thing you could do is you could actually use a method where you only have a small number of these samples, and you have some kind of a suitable generative algorithm can generate more samples of the similar type.
Right.
So you don't painstakingly try to create these samples from scratch.
Yeah, but the problem with training is if you're generating samples from the given if you have a prior, then what happens is you will not get to witness, or you will not get to see discontinuities or non-smooth structures which are rare. So then what will happen is if suddenly your network comes across a very rare phenomenon, it will not identify it.
Sure. So in that case, so if you do intend to solve problems which have such a rare occurrence of these kind of structures, you would like to push those structures into your training set. Of course,
but you have not seen them.
No,
so we tested.
Them. So we have. So for instance, these problems we tested on Berger's equation, linear advection. We tested shallow water equations, Euler equations, and all sorts of initial conditions with that smooth and discontinuous structures in it, and it worked just fine. Of course, if you really want to sit and try to break the network, I'm sure there is some initial condition to break it, but we haven't seen one that breaks it thus far.
Okay, all right. Next to the many query problem.
Yeah.
So there were two approximations, if I understand. One was basically replacing the L by its surrogate L star.
Yeah.
And then there was this approximation of the measure, the push model.
Yeah.
Right. So now you also can you go to that theorem wherein you mentioned the order of the error? Yeah. So here, yeah, I missed seeing this for a little while. Just hold on here.
Sure, I'll wait here. Yeah.
Okay. I see. So in the subsequent numerical implementations that you showed, I mean, because you are saying here like a big O, so is it like really tight, or is it can this be improved or something?
I'm sure it can be improved. This is still a loose bound. I mean, it has to be an epsilon order approximation. That's what we're saying. We're not worried about the actual constant sitting in there. But as epsilon goes to 0, these would.
While I was actually writing down this question, you already answered that question because my question was basically a rate in terms of the parameters involved.
Yeah.
So you kind of answered by giving the cost function.
Yeah.
So actually, I was thinking that in terms of the cost function, also if you change your surrogate L, so in like how expensive it is to get so to say nicer surrogates. Nicer in the sense which respect a little bit of the geometry or the structure present in the setup.
Well, I mean, so I can tell you that the network we used here typically had around 1,000 parameters. That's it. It's a very, very small network. Of course, you could take a much larger network, and that would capture more features. But here we're trying to approximate just a scalar value. You could also train a network to directly approximate the flow field, right? And there you would need a bigger network to do it. And that also, I think, has been done by Sid Mishra and his group, and it works quite well even in that case.
I understand.
But there, of course, the regularity of oscillation goes down because now you're working with BB functions.
Correct. Okay, so can you go to the plot wherein you were showing the prediction and the actual? Yeah, this one. So here, I have a problem with this plot in the sense like you were saying that this is concentrating around the line. But my plot
diagonal,
yeah, but the point is that if you do not tell me the actual magnitude, then if I zoom in, then it will be very far.
So that's what I'm giving over here. So
yes, exactly. So this I missed. So I was just I had written it down that where is the standard error.
Yeah, of course.
Okay, all right, thank you. Can you now go to the last part, the inverse problem? Yeah, here. So when you are introducing this GAN, aren't you like at some level trying to find some a lower dimensional structure already? Because I mean the entire thing is basically you introduce this NZ, which is much smaller than the NX.
Exactly.
And so if you are already doing that, then put very bluntly in the sense that you are already reducing the dimension. So what happens is the MCMC, the usual MCMC, which has this problem of NX, which is basically like it scales very poorly when N is high. that itself is gone, because effectively we are trying to say that we are trying to approximate this very high dimensional MCMC object by reducing it to a very lower dimensional object, which is NZ.
Right.
So isn't it at some level also telling me that there is a smoother structure present in the image, and I want to actually identify that. And if I am doing that, then why don't I straight away assume that the noise itself has some sort of a correlation structure, and then what will happen is your MCMC will not scale like an X. It will basically be just okay, because there are these MCMC algorithms which are built in infinite dimensions, and the simple idea is that the noise basically you take when you are considering finite dimensional Bayesian inverse problems, the noise that you take is basically IID noise. And the moment you take IID, the sum, it is basically the trace which plays the role over there, and the trace determines the dimension, and which is basically the trace which is coming in the error term also. So if you have this correlated or like a very nicely correlated Gaussian field, then what will happen is you can actually get rid of this NX problem. So have you thought along those lines, or is it just like okay, because this works, so we'll just
well, I mean, I'm sure there are other ways. So essentially what you're saying is there are other ways of also reducing or inferring a lower dimensional representation.
That's what I'm trying to say. Yes.
So GAN is one particular way of doing it. If there's another method that you know how to do it, I mean, you plug in that one as well. But the challenge is, I mean, when you're dealing with data like this, it's very difficult to figure out what this low dimensional representation should be. So what we are doing with the generator is almost learning a flow map that's going from a lower dimensional multivariate Gaussian distribution to something which looks like this. And you're learning this flow map, and that's what you're kind of plugging in to get everything at the lower dimensional.
Yeah, setting. But what I'm trying to say is that when you are saying that you need to understand, I mean, you need to identify like for which one is it going to work, that basically will come from the problem at hand. For example, if you were particularly looking at this, the specific PD, right? When you are identifying kappa.
This one, yeah.
When you're estimating kappa. Yeah. So there, basically, I mean, what's his name? Andrew Stewart. He has this entire, so he has this big Bayesian inverse problem node in which he identifies all these operators specific to a specific problem, and then identifies the corresponding covariance kernel, which is basically driven by the forward operator.
Right.
And basically like the entire recipe is given.
Yeah. So then you can look at the low dimensional approximation of this covariance kernel, looking at the spectrum.
So what I was asking was that have you looked at it and have you compared how do these two behave without using the GAN?
No, we haven't done the comparison, but that might be interesting to do. But of course, the advantage of something like this is that even for something more complicated than the simple PDE, you could still use the same kind of GAN architecture and still make it work. But there you'll actually have to figure out what is the corresponding covariance structure for that particular PD problem. For instance, we've also done this for integral equations when you're doing radon transforms and things like that. So even there, you could use something like this and it works really well.
I see.
If you can find the underlying structure of the covariance matrix, sure, you can. If you can figure out the eigenstructure of that, you can even use something like that.
Right. Okay, great. That's all. That all answers my questions. Thank you.
All right.
Thank you, Deep. It was a wonderful talk. Thanks.
Thanks.
So can I jump in?
Please go ahead.
Okay, thank you very much. Saram Denshapal Sara, I really enjoyed your talk. Great talk. Thank you very much. So I have several questions, and I was just hoping I could get some of them in. One of them is that DG schemes also have rich information at the boundary and at the interface between the boundaries. Do you also incorporate that, or do you just take model functions which indicate trouble within the zone and use that for tagging?
No, so trouble cell detector, the way we actually did it is we didn't look at just a solution in the cell. We actually looked at the neighboring cells as well. So in 1D, we actually looked at 1D problem. We looked at the mean value in each of these three cells and the value at the boundary. So we kind of plugged all of these together to get a context of if there's actually a physical oscillation or if it's a spurious oscillation.
Okay, so let me push forward then on this same question, which is to say that now there are very efficient predictor steps within a zone which are like Adder schemes, which will actually go ahead and predict the solution based on the physics of the PDE. So you can actually take the predicted solution at time tn plus 1 from time tn to tn plus 1 and say, how did that match up, or how did that square up with the corrected solution that you got at the end of the time step of tn plus 1? And you can use that as a criterion for actually going ahead and incorporating the PDE, because all you've incorporated so far is patterns. And saying, I'm conjecturing that this pattern is a troubled pattern, that pattern is not a troubled pattern, and then you're going forward. This gives you a much richer piece of information about not just which patterns, but how they incorporate the PDE. Have you considered doing that, and would you be open to considering it further at some point?
Absolutely. Perhaps that might be the way to go if you're looking at 3D problems, because after a point, you may not be able to construct these canonical functions. And of course, the catch there is that now you're talking about solutions that are coming from a specific conservation law model. Right now, we are assuming that it's not dependent upon any specific solution of a conservation law, and because the same network works for all conservation laws. However, we've also seen for certain examples that if you're able to do this just for linear advection and burgers, we did this for artificial viscosity, that's good enough for all other conservation laws like Euler equations and shallow water. So you can use it on some basic conservation laws, use this adder approach to figure a richer class of functions and train the network accordingly.
Okay, so maybe we should take this up at a later date if possible.
Absolutely.
Especially because it kind of coincides very nicely between your interests and mine. I mean, maybe we can, you can drop me an email, or I can drop you an email, and we can pick it up at that point. So let me then push forward on this same line of reasoning, but give you a dramatically altered counterpoint, which is to say that consider two mimetic systems, which are blood brothers of each other, namely the MHD equations and the Maxwell's equations. Difference is that MHD is highly and strongly nonlinear. So it fits within the paradigm of what you've done, which is shock capturing schemes for Euler type equations. Maxwell's equations is a very different beast. Why? Because you can actually have a DG scheme for Maxwell's equations, which for most parts of the domain will actually work almost without invocation of limiters. So the invocation of the need for limiters is very rare. On the other hand, very valuable. And basically, there is where a unlimited DG scheme can shine most of the times, because the less you invoke the limiter, the more you're closer to the spectral accuracy, which is what this Maxwell's equation is all about. So have you considered situations like that, where A-B contrasts between a scheme which has one thing and a scheme which has another thing?
Not really. So let me ask you this. For the Maxwell's equation, is it correct to say that if there are any discontinuities, they'll travel mostly as contact waves? Is that correct to say? Versus the shock?
Not really. There are no, for typical computational electrodynamics problems, which are on reasonably well-resolved meshes where the mesh structure can be predicted, you don't have these contact discontinuities developing.
Yeah, and that would be worth investigating then. If there are some schemes that inherently work without, but then I would assume that the solution structure is inherently smooth for MHD versus
for
Maxwell
smooth for CED, except in certain circumstances and in certain regions.
So then I think it will be important to identify what are the revealing features that can capture something like that, and kind of tell a network that, okay, if you see something like this, don't flag the cells. So there has to be a richer notion of what features should actually be used to classify cells as good as bad.
Sure. So we could take this up as a later issue also. So let me then ask a third type of question, which deals with the second part of the topics that you were discussing in your talk, namely, you have a model and you have an answer for maybe 100 airfoil cases, and you want to predict 1,000 airfoil cases. How small can that number be? I mean, can it be 10? I mean, of course, you're willing to tolerate a greater error in your answers, but that might be an acceptable situation. And to just kind of give you a practical instantiation, in astrophysical simulations, for example, the simulations are backbreakingly difficult, not just 7 hours on a computer, but maybe 70 hours on a computer. But what is extracted is a small piece of information at the end. And I'm interested in showing that, and so people cannot afford to do 100 calculations and they don't have a library of 1,000 calculations. But I'm interested in showing if you have maybe 10 or 15 or 20, and you're willing to tolerate a higher level of
noise or error in the
error at the end. Yes, you're willing to tolerate a higher level of error because there one doesn't want, one is not optimizing then an airfoil shape or something like that. One is just saying, okay, generally speaking, this would do this and that would do that. Can you work with samples of 10 or 15?
I don't think we've ever tried with that lower sample. And I would say that if you actually do want to work with something as small as that, then this is where the whole notion of these pins comes into play, where you actually have to put in additional constraints which sort of brings in the PDE at the level of the training. So that reduces the load of the number of samples you need to train with. So you need to put in other constraints to kind of tell the network to search in a more constrained manifold to kind of find the approximation does it want. But otherwise, something as small as 10 or 12 with neural networks is going to be hard, because in general, neural networks are very data hungry. So 10 or 12 might become difficult unless you do something more.
But what if the physicist has some prior intuition worked out, which he kind of gives you to kind of train the network?
Sure, if you can use this prior intuition into either build it into the architecture or the loss function, that can definitely help reduce the number of samples you need to train with.
So that is good. That is good. So then that brings me to my last question, which is to say that how black box is this if one wanted to make it black box? And what is the difference between black box approach and expert driven approach? I mean, eventually the hope is that the two are almost similar, and experts like you will go and do something else or find even richer sets of problems to work on. But this just turns into a black box technology. Already MATLAB offers some sort of black box capability for artificial intelligence, right? So how black box can this be?
So I would say that, I would say that something like trouble-cell detectors and all are pretty much like a black box, because at that level, you're just doing pattern recognition. You're not doing anything more than that. So, and if you can test it across a number of examples where it works very well, then you can treat it as a good black box to use. And this, whatever we train, can actually be used by any other code. You can just take this network, plug it into any other solver that you want, and start running it. And people have done that, and it's worked well. But the other examples, of course, it's a little less black boxy, because there is some more theory to support and tell you under what circumstances can you actually expect it to perform well. And I think that's eventually the kind of space that I would like to be in, where you're not just using it as a black box, but you're also able to support it theoretically to some extent and say how reliable it is.
Okay, fantastic. Thank you very much. Thanks.
Most welcome.
Are there other questions from the audience?
I see one over there. Yeah.
Yes, go ahead, Arpit.
Thank you. So my question was about the theta that came up in the first part, the min mod limiter.
The min mod limiter.
Yeah.
You mean the M, you mean, right?
Yes, but there was a theta which you said if it's less than 0.5, we assume that the...
Okay, right. You're talking about this one.
Oh yeah, sorry, it's a
Y hat.
Yeah, sorry.
Yeah.
So I wanted to know if there is a scope for a hierarchical limiter here, or like suppose that if y hat is greater than 0.5, you say that it's a trouble set. But what if it's between 0.5 and 0.6? Is there a scope for doing like a min mod limiter would reduce it to something like first or second order? But if it is only between 0.5 and 0.6, maybe we would like to reduce to second order. And if that is, or if there is any general idea of doing hierarchical limiter in such a situation.
I think you can build it in. Basically, what you're saying is instead of having just two classes as good or bad, You want to kind of have 3 or 4 classes, and you can actually do that if you can correspondingly create the training set for that. So for some of the applications which I couldn't talk about, right? For instance, are you doing this P adaptation, or you're doing artificial viscosity for spectral schemes? Here we actually train networks to actually tell you what is the regularity of the local solution. Is it discontinuous, C0 but not C1, C1 but not C2, and so forth. So you can have these different classes, and the basis on what kind of regularity you have, you can have a different order of limiting in that area. So you can definitely have something like that.
Yes. Okay. Okay. Thank you.
Please go ahead, Jacob.
Yeah. Hi. So
I lost your voice there. Could you repeat that? Is it just me or
No, none of us can hear him.
I see.
So maybe you can, if you can hear us, you can type the question in your chat.
Okay.
Yeah, he's
Thumbs
doing
up. All right.
that.
In the meanwhile, if anyone else has a question, I'll be happy to answer that.
Yeah, so Deep, if you still have some energy, this is Ujjwal here, Deep.
Absolutely, I have all the energy you need. Yeah, go ahead.
Okay, so I have just a naive question.
Mm-hmm.
So, so you are using these neural networks to compute different kind of PDEs. So, for example, you are also computing compressible Euler.
Mm-hmm.
So, so at the end of your computation, you are getting a solution. How do you conclude that's the correct solution?
So so which application are you talking about? Say that one with the trouble cell detector, for instance?
Yeah, I mean, you take any of your approaches and let's say you are computing solutions of compressible
So it's different. So for instance, the first application, you're still solving the PD using a DG scheme. That doesn't change. All you're using.
No, I'm not. Yeah, so let me rephrase my question. I'm not getting into the details of your schemes. So you use whatever your favorite scheme and you compute something.
Yeah.
So my question is that how do you conclude that's the right solution?
Well, I mean, in this case,
or in other words, what are you computing at the end of the day?
I mean, okay. So let me talk about one problem at a time. For the first problem, all you're doing is you are replacing another way of detecting trouble cells with this way of detecting trouble cells. But the solution, approximation, and accuracy will be the same as what the inherent DG scheme or finite volume scheme is giving you. That you're leaving untouched. So it's the finite volume solver that's actually giving you the solution. The network is just helping to enhance the solution. That's about it. And in terms of actually knowing whether it's the right solution, for most of these cases, you'll compare it with a reference solution. If you're seeing that it matches up, it's the correct solution. If you see oscillations and it's bad, then it's not the right solution. But I guess what you're asking is if you use a neural network to directly approximate the full solution of the PDE, instead of using a solver, you're using a neural network to get the solution itself. How do you know if that solution is the right solution? And that'll, I think, be even more important if you talk about conservation laws. Is this supposed to be the right entropy solution? Is this supposed to be converging to the right entity? I don't think we can say all those things at this point. The only thing that is typically known about these, when you use deep learning for problems like this, is you're minimizing some PD residual, which is kind of strongly posed. In the strong sense, you're reducing the residual. But of course, as soon as you end up with discontinuities and shocks, the question can always arise whether you're actually capturing the right solution. And recently, there are some groups who are actually formulating these neural networks to solve PDEs using the weak formulation. And you're slowly moving towards a setting where you can say something more about when you're converging to a solution, what can you say about the solution you converge to? But I should also mention that on paper, everything looks nice. The biggest problem is when you're actually training these neural networks using an optimization algorithm, you have literally no control over what you're going to get. Theoretically, on paper, you can write, well, this is what the error should be, assuming things trained well. When you actually start training a network, all bets are off. So what we don't have in that case is, like, for instance, we have these nice entropy stable, this entropy stable theory for numerical schemes for conservation laws. You don't have anything like that for optimizers. So there's a big disconnect between what you actually train and the theory that you're developing for neural networks to approximate solutions. I don't know if that answers your question.
Well, I mean, thanks for your explanation. But my question was, even your entropy stable scheme, I mean, in view of these recent theories, I mean, they're useless, right? In some sense, because you don't know, for example, Euler equation has unique solution or not. So my question was little, the question is that at the end of the day, what are you computing? Are they really solutions? I mean, you are struggling with, you are innovating several approaches and, how efficient they are. But at the end, what are you computing?
Of course, then, I mean, if you're asking for things like Euler equations where you don't even know what the true solution is, you could have many entropy solutions. I mean,
exactly.
I don't think deep learning is even close to answering any question like that yet. Right now, all you're able to do with deep learning is develop fast surrogates for some other problem where you're not worrying about whether this is in some weak sense the correct solution. All you're saying is that up to some error, you're going to get very fast medium resolution solutions, which you will eventually use for something else. But to actually ask as to what solution you're getting, I don't think you can say anything right now. You're far from saying anything over there. But that's why you have to judiciously use neural networks. You just blindly use it to solve a PDE, because then you don't know what you're converging to. I completely agree with you there. You have to be careful about how you use it.
Thank you, Deep. Thank you.
I see the question in chat now. In the first part of the talk, after detecting bad cells, how do you fill the data for reconstruction? Okay, so you're asking about how we actually do the limiting. Is that the question, Jay? So assuming that is your question, so the limiter, I guess in this case, we're using a standard TVB type limiter to limit the solution, or you could use any other limiter that you want. So this limiting can be any standard limiter that you use in practice. All that the network is being used for is just to figure out where the limiting should be done. So you can limit using any traditional approach that you want. You can use a Vino limiter if you want, but that's a very expensive limiter, which is also why you would want to be doing the limiting only in the correct cells. You don't want to be doing it anywhere where things are smooth. So that is up to you. You can pick any traditional limiter. The network is only telling you where to limit. Okay.
Are there any other questions from the audience? Thank you very much, Deep, for this wonderful talk, and also for all the energy to answer our queries.
No, it was my pleasure.
It was wonderful having you. I guess.
Thank you for inviting me as well.
Let's thank the speaker for this wonderful talk.
Yeah, we have virtual claps now, right? With emojis. That's the new norm now.
I find this extremely awkward. I would rather skip it, but we should thank you.
Yeah. Well, hopefully you won't have too much more of this. We'll hopefully move back to more normal talks in person. Right? That's
nobody can tell. Nobody can tell. But yes, hopefully. All right, Deep.
All right.
See you later.
Thank you so much.
Bye-bye.
Bye-bye.